Hi, I'm Luke Collins from the Tech Design Forum, and I'm here with David Abercrombie, who's Program Manager for Advanced Physical Verification here at Mentor Graphics. And we're going to talk a bit about the impact of double patterning on the design process and the yield process. So if you could briefly outline for us, what is that double patterning, why do we need it, and what are some of the issues around it?
Okay, double patterning is, in many aspects, just the next thing under the design for manufacturing title, in the sense that it's something that needs to be done on the design side to accommodate constraints on the manufacturing side. For many years, that's been primarily OPC, in terms of being able to print the shapes that you draw on a layout.
Right.
The difference in OPC versus this new trick of double patterning is that with OPC, the designer didn't have to know what happened. They drew it normally. OPC happened later.
It was decoupled from their concerns.
From their concerns.
It's one of these over-the-wall moments.
Yes. With double patterning, that's different in that it's very likely, if you drew it normally, you would draw a situation that could not be decomposed into the two masks.
Right.
So you have to account for that while you're doing the design. So that's why it's moved into their space.
And as I understand it, just so that we've got the basics, the requirement for double patterning is that it's that good high school physics about diffraction.
Yes.
It's to do with the fact that the illumination source is 193 nanometers,
yes,
but you're trying to produce features on chip down to 28 nanometers, 20 nanometers perhaps.
Yes, at 20 nanometers with 193 nanometer lithography, even with every OPC trick in the book that we know of, there's no way to resolve the dimensions in the images that you've drawn. And that's why this is, unlike other DFM things in the past, this is not a do it because you should do it. This is do it because you have to do it. It's mandatory.
Yeah. And as I understand it, the minimum pitch where between lines is about, what, 80 nanometers or something?
Yeah, 60 to 80 nanometers, essentially at the 20 nanometer node. At 28 nanometer, you don't need to do double patterning, but starting at 20 and below, you're going to have to do double patterning.
Okay, so we've got this requirement to work harder at understanding the impact of the physical manufacturing process, and we need to wrap that up and bring it further up the design process so the designers, the logic designers, have got a better idea about it. What sort of gotchas should they be looking out for?
Okay, well, first of all, they need to understand and discuss with their foundry provider, how is this new requirement going to be input into their flow? What kinds of ways is it going to impact what they do, both in the custom layout and the place and route environment? And depending on which foundry you use, there are different options in how you might see this impact you. There are two fundamental flows. Either one flow is where the designer is responsible for crafting the two layers, so that they would tape out the two mask layers, and then the fab just creates the mask from them. The other basic flow is where the designer continues to draw in a single mask. It's decomposed on the fab side, but he's just got to verify that what he's drawn is decomposable.
Yeah.
Okay, so they're clearly...
So this is about handling this process of taking a design which would normally have been done on a single mask and splitting it into those two masks so that you can do two patternings and you won't get the interference effects which otherwise would blur any features pitched at less than 80 nanometers.
Yes. So what they're going to see as requirements are two potential things. A, they're going to see new checks. In design rule checking, for instance, that will check whether what you've drawn can be decomposed.
Yeah,
that's the first thing they'll see.
That's a very uncomfortable moment when that comes back and it can't do that.
Yes.
Sorry.
And that's our job as an EDA vendor, is to make that as easy to understand and fix as possible.
So have you got diagnostic tools, diagnostic feedback in your offerings, which make it really obvious to the...
That's what we've been investing a lot in, is not just finding the error. Anybody can say it's wrong. It's how to display that result and give you additional information to help guide you as to what to do about it. And We've even patented some technology, these hints or warnings we call them, that when you have this violation, it gives you additional information to let you know what changes would get you into new trouble, what changes seem to be the most optimal to make sure you don't incur additional problems, and to help guide the custom designer into making the appropriate changes.
And these are done graphically?
Yes.
So I see a violation area, I see sort of options for moving parts of the layout.
Yeah, you see that these in addition to the error marker, which is a more traditional thing you're used to in DOT, you'll see these warning markers, which are just additional markers that are giving you additional information over, stay away from this, go here, do this kind of thing, to help guide them in that process.
Right. And the implication to me of all this is much greater collaboration is going to be necessary, a much more intimate understanding between the designer trying to get some logic turned into some poison silicon and the fab trying to make the silicon for the designer. So are there new ways of thinking about that relationship, or new things that you can do with the tools to enable that kind of collaboration?
Well, certainly the collaboration requirements are greater. It's a tighter integration now between the process and the design. That this is just another link connecting the two, and that requires tighter collaboration both between us and the foundry requirements for this and the designer on how to use it, and then between the fab and the design community on, okay, what flow do they expect, what outputs do they expect them to provide, and
right.
So we've had a lot more mutual discussions and meetings, and which is just the evolution of how things have gone in general. At these tighter nodes, much more collaboration is inherently required.
Right. So would you say that's mature now? This, you've got the requirements for the designers to understand that they need to understand more of the physicals. Right. You've got, the willingness of everybody to talk together more. You've got data flows, interfaces, all those sorts of things. I mean, how are you doing, do you think, on getting to the point where this, the problem is hard, but we're doing everything we can to make it easy?
I think at 20 nanometers, it's pretty close to being done. We've got the tools are working, the techniques are working, we've validated the flow and the capabilities. I think what's left is it's so early in the ramp. There's still a lot of people that don't have to come up that learning curve to learn those new things. I think that's the only thing left at 20 nanometer. I think where there's still work to be done is looking now at 14.
Right.
We're going to need to do triple patterning, sidewall image transfer, these other new techniques that will introduce new challenges.
Right.
That's just beginning, and we're obviously working on that already. But I think 20 nanometer, I don't foresee any problems. I think it's going to work. I think the people are going to know what to do, and it's going to be a success.
Well, excellent. Thank you very much indeed for that, David. I look forward to seeing the 20 nanometer chips come out.
Me too. I can't wait to buy that new consumer product.
Thank you.